it is really helpful to think about simple harmonic motion in terms of energy. And at this point, we're going to continue to think specifically about our mass on a spring, but a lot of this is actually going to be general for all types of simple harmonic motion. So we've said that A represents the maximum position from equilibrium. And keep in mind that, again, we've defined x equilibrium to be equal to 0. So at the maximum value, the total energy is equal to the potential energy. At that point, it stops and turns around. But we know that energy is going to be conserved. Again, this is an isolated system without friction or air resistance. When you're at x equals 0, in this case, there's no potential energy because the spring potential energy depends on the distance you are from equilibrium. But at the very center then, all of our energy must be equal to kinetic energy. So we use two positions to think about this. At the maximum distances, the turning points, we know that all of our energy is potential energy because at that point it's stopping and turning around. This is just the idea of maxima or turning points. And in that case, our spring potential energy is 1/2 k x squared, where x would be the distance we are from equilibrium, and we know that the distance we are from equilibrium is a. So there you go. And because it's a squared, it doesn't matter whether you're at the negative a or the positive a. But then at x equals 0, that equilibrium position, we have that spring potential is 0, and we can relate this back to the maximum speed. We know the fastest that this is ever going is at the center point, because otherwise some of your energy is in potential energy. So what is the result of this? We can actually do some really important restrictions then of what's going on in this system. We know from energy conservation that these two things must be equal. So this tells us now that there's going to be a relationship between the amplitude and the maximum speed that our object is ever going. So let's now go back and relate some variables. Previously, we also related maximum velocity to other variables as well, because we knew that when we took the derivative of the position equation, we got the velocity equation. So we can now actually start by just using this one. We see that the factor of 1/2 is on both sides. We can cancel that. We then rearrange and solve for Vmax. So Vmax is equal to the square root of k over m times the amplitude. Well, k is our spring constant, so that is defined by the system. M is the spring constant, is the mass of the object on the spring. So really, this first term is defined by the system. However, A, the amplitude, we said can kind of relate to the initial parameter, like where have you started it at? And that's also what Vmax seems related to. So, okay, we have part of it from our system, but now we have two other things. But right now, note that we don't have time anywhere. And this shouldn't surprise you, because whenever we work with energy, time doesn't appear. Energy is about your initial situation and your final situation. And before, our equation of motion had time in it. Okay, so let's combine some things together. We already knew that the maximum velocity was equal to 2 pi times our amplitude divided by period, or we can express it in these other forms based on the relationship between frequency, angular frequency, and period. So I can now come back and plug in this form. Again, omega is going to be what we use the most mathematically because it just has the fewest terms. We can plug this in for Vmax. You now see that there's an A on each side. So we get to simplify this down. Well, before, we didn't actually have a way to define what our period was. And again, period is related to frequency and omega. So now we actually see that I can define what the period of motion is going to be in terms of variables from my system. Now there's something really subtle here. This period is how long does it take to get from one point in the motion through a whole cycle back to that same point. Notice that this is completely independent of the maximum speed or the amplitude. So again, omega and t are just different ways of really talking about the same thing, and it actually only depends on the system itself. What is your spring constant and what is your mass? So if you have the same mass and the same spring, and you displace the spring a little bit, and let it go, you have a certain period. If you then stop it, displace it a different amount so that it has a different amplitude, you actually are going to end up with the same period. And this is going to be something that is fairly general for simple harmonic motion of different types of systems, that there's going to be something in your system that defines the frequency of motion, the period of oscillations, how you start that system, how far you displace it, or what maximum speed you give it, actually isn't going to affect the period, or again, the frequency. So this is a really important result, and one way to think of it is using conservation of energy. There's a mathematical way to get to the same result, and we'll do that in the next sequence of videos. So coming back to conservation of energy, we now can think about the time and how energy is changing in time. Now remember that our traditional energy diagrams are potential and kinetic and total versus position, and now we're doing it versus time. So this is a plot of energy, it's not an energy diagram per se. So at any given point, x, we know that the sum of our kinetic energy and our spring potential energy has to equal our total energy, which we can express in two different ways. This actually means that you can relate position and speed once you know one of them. So if you know what position it's at and you know your other variables such as spring and mass, you can actually relate your velocity back if you knew anything about your initial conditions, or again, in this case, your maximum position or maximum speed. So a different answer is that if we know about one position, one place, even if it isn't your initial condition, that's sufficient to define what's happening in a different place. So if you have your initial speed and your initial position, or if you have your total energy in any way, you can actually then relate these to any other place. So you might not need your initial conditions depending on what other information you're provided. So something to think about is that this actually goes up and down faster than just the position. And the reason for that is that if we look at, say, the potential energy, so U is coming from this delta X, and in one case it's positive, and in one case it's negative. But U, our potential energy, which is in blue, doesn't care. So it has a maximum at both of these points, even though here in position it's maximum and here it's minimum. Where you have a minimum in potential energy is going to correspond to your zero of position. So if you are trying to sketch out what's happening in energy, keep in mind that the curve actually looks a bit different here. So it's going twice as fast, or technically, so the best way to think about it is that it's oscillating twice as fast, but one reason for that is it's oscillating between 0 and maximum. This is oscillating between positive and negative.